All right, guys, section 3 of chapter 6, Riemann sums and definite integrals. Let's get going on this. So what we want to do today is understand the definition of a Riemann sum, evaluate a definite integral using limits, and evaluate a definite integral using properties of definite integrals. So let's first talk about those Riemann sums. In the definition of area, the partitions have some subintervals of equal width. This was done only for computational convenience. The following example shows that it is not necessary to have subintervals of equal width. Okay, so the whole point in the next example I'm about to do is to show you that your subintervals don't have to have the same width, yet you can still get the area with the limiting process of a Riemann sum. So let's look at the region of the graph of square root x from 0 to 1 in this picture. Okay, what we're going to do is evaluate this limit of the Riemann sum where ci is the right endpoint of the partition given by I squared over n squared. Okay, so it's not just given by delta x plus, whatever, or delta x times whatever I you're on. Okay. Delta xi is the width of the ith interval, but you could see that the first rectangle is pretty thin, then they get thicker and thicker and thicker and thicker in general, okay? Don't get stuck on this formula right here. That's just a formula that they kind of pulled out of thin air, sort of, to make the subintervals not be all the same width, okay? It's not like you have to memorize a new formula or relearn something. This is only to illustrate the fact that you do not need to have subintervals of equal width to get the area. So the width of the ith subinterval is given by delta x, which is I squared over n squared minus I minus 1 squared over n squared. So it's like the right endpoint minus the left endpoint of the subinterval gives you the width of the subinterval. The reason we had to do it this way is because each subinterval is different, has a different width. Okay? So if I FOIL this out, subtract, simplify, I would get 2I minus 1 over n squared, and that's what my delta x is. So the limit is f of ci delta x, and ci was I squared over n squared, so that's inside the square root, times delta x, which we just got the formula for here, 2I minus 1 over n squared. So that simplifies to 1 over n cubed times the sum of 2I squared over minus I. How'd that happen? Well, the square root of I squared over n squared just simplifies to I over n. And then this n multiplies this n squared right here to give you n cubed, and then they distributed the I to give you 2I squared minus I. Okay, so that's just a quick algebra on that. Then I can break this apart as two separate terms. So 2I squared minus I squared is separate terms, and then use the sum formula for I squared and the sum formula for I. So it's 2 times the sum formula for I squared minus the sum formula for I. Okay, I FOIL all of that out and distribute, combine like terms, subtract, distribute the n cubed to the denominator, and this is what I get. And the limit of that is 2/3. If you break this up, you would get 4n cubed over 6n cubed plus 3n squared over 6n cubed minus n over 6n cubed, which simplifies to 2/3 plus 1 over 2n minus 1 over 6n squared. If I take the limit as n approaches infinity here, this term and this term both go to 0, and that's how we got 2/3 there. Okay, the region shown in figure 6.18 right here has an area of 1/3. Because the square bounded from 0 to 1, like this square has an area of 1, you can conclude that the area of the region shown in figure 6.17 is 2/3. Okay. So that's just kind of like a further proof that the area of this region is actually 2/3. If I get the area, if I take the area of this square, which is 1, it's a 1 by 1 square, and this is the area under the parabola x equals y squared, which turns out to be 1/3, then if you subtract 1/3 from the area of the big square, you get the area that remains, which turns out to be the area under the square root graph, which would be 1 minus 1/3 is 2/3. So we're just validating that our answer is correct. So this agrees with the limit found in example 1, even though that example used the partition having subintervals of unequal width. The reason this particular partition gave the proper area is that as n increases, in other words, the number of rectangles increases, the width of the largest rectangle has to approach 0, the width of the largest subinterval. This is the key feature of the development of the definite integral. The limit of a sum was used to define the area of a region in the plane. Finding area by this means is only one of many applications involving the limit of a sum. A similar approach can be used to determine quantities such as arc lengths, average values, centroids, volumes, work, and surface areas. The following definition is named after Riemann, a mathematician. Although the definite integral had been defined and used long before the time of Riemann, he generalized the concept to cover a broader category of functions. So in this following definition of a Riemann sum, note that the function f has no restrictions other than being defined on the closed interval a,b. The function f was assumed to be continuous and non-negative because we were dealing with area under the curve. But for a Riemann sum, the function does not have to be non-negative and technically does not have to be continuous. So let f be defined on the closed interval a to b. It just can't have horizontal gaps in the function because it has to be defined from a to b, but it might have a discontinuity in there. It might have like a jump discontinuity or something like that. Okay, and let delta be a partition of a to b given by a is equal to x naught, which is less than blah, 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 all the way up to xn, which is the right endpoint, where delta xi is the width of the ith subinterval, so xi minus 1 comma xi. So that's just from a left endpoint to a right endpoint of some partition in here. If ci is any point in the ith subinterval, then the sum of I equals 1 of f of ci delta xi is called the Riemann sum of f for the partition delta. The width of the largest subinterval of a partition is called the norm of the partition and is denoted with a little triangle with 2 vertical bars around it. If every subinterval is of equal width, the partition is said to be regular, and the norm is denoted by the norm is equal to delta x, which is our normal definition, b minus a over n. For a general partition, the norm is related to the number of subintervals a to b in the following way, that it's b minus a divided by the norm, which has to be less than or equal to n. That's a general partition. So the number of subintervals in a partition approaches infinity as the norm of the partition approaches 0. That is, as the norm approaches 0, in other words, the width of the largest subinterval, as that approaches 0, okay, that means that the thickest rectangle is getting thinner and thinner and thinner. That means that you're going to have to pack an infinite number of rectangles in that finite region in order to fill it up. So the converse of this statement is not true. So in other words, as the number of rectangles approaches infinity, it does not necessarily follow that the norm has to approach 0. Okay? Slight little semantic detail there, not going to be a huge deal. So the converse of this statement is not true. For example, let delta n be the partition of the interval from 0 to 1 given by 1 over 2 to the nth power. Okay? So as shown in the figure, for any positive value of n, the norm of the partition is 1/2. So letting n approach infinity does not force the norm to approach 0. In a regular partition, however, the statements norm approaching 0 and n approaching infinity are equivalent. Okay, so just a little detail there. All right, that's it so far. Stay tuned for the next video.